These are really fall into a couple of categories, but I've broken this down into topics that relate to inadequate drive of the device and the inability to support the necessary current. So follow along. I think you'll understand why these are the key factors that make a big difference in a successful design or not. I'm going to begin with looking at the pulse and continuous current ratings of two devices: traditional silicon that we've all been using for decades versus GaN, which is the new kid on the block. It's very high performance transistor. One of the key areas where you'll see big differences are in the peak current handling capability. So I've made a chart here overlaying. Let's start with the device. So this is a CoolMOS big silicon transistor, 51 milliohm rated at 25 degrees C. It's rated at 25 amps at 150 max junction temperature, versus the GaN device is also same range, a little bit higher, 55 milliohms at 25 C, also rated identically for drain current, right? So it's more about the thermal performance, the thermal conductivity that sets the drain current. The key difference here is in the pulse current. Notice that at 125 C, GaN only has a pulse current capability of 36 amps. Silicon at 150 is 148 amps. So this is a really big difference. This results in maybe some confidence that when you're using silicon, if your current measurement is a little bit slow or accuracy isn't quite there, you don't have to pay that much attention because it'll take it as long as I keep my junction temperature under control. With GaN, and the reason I've showed these curves of RDS(on) versus current here is you can start to see where some of these differences occur. If I look at silicon, that's these lines here. If I extend them up, here to 150 roughly is where it's pulse current rated. I'm at a pretty high RDS(on), 0.2 ohms, where it started out here at less than 0.1, but at least it's still conducting. Whereas with GaN, you reach a saturation point known as current collapse. You can't probably read the numbers here, but you can see the shape of the curve. With the highest gate drive, you reach a point where the RDS(on) is just going in a vertical line. So there's no way I can even get to, say, 100 amps here. The transistor simply isn't going to support that level of current. So this is what I have to watch out for, and maybe it's a bit easier to see if I show you what current collapse looks like when you try to turn on the transistor. So I'm showing here a classic double pulse test circuit. Q2 is the device under test, so this is the switch we're turning on, and I'm measuring current in the transistor, not in the inductor. This is actual transistor current. Actually, I have both here on this chart. And the high side is simply a freewheeling diode, so I'm allowing recirculating current to go here, but I never turn this device on. So we start at 25 C, bus is at 350 volts. Now the inductor is a really small value, it's 1 microhenry, so the current is going to ramp up very quickly, as you'll see, and I'm driving the gate with its nominal steady state gate drive current that we're supposed to drive it with. And you can see what happens here. So this is the VDS here of the transistor, starts out at 350. I turn it on, it drops down to near zero. Meanwhile, now the current, you can see both the transistor current and inductor current match. They're tracking here at 10 amps per division, so 10, 20, 30, 40, 50, 60, 80, more than 80 amps. I think what you're seeing here is the current probe is starting to saturate, but meanwhile, look at what's happening to VDS. Once I reach about 60 amps, VDS is suddenly starting to exponentially increase here. So you can imagine the power dissipation. If I were to multiply V times I here, it's really getting out of control. And especially here, once I fully hit desaturation, this is just like an IGBT in desaturation, same kind of mechanism occurs here, and the transistor can no longer support this level of current. And matter of fact, it even folds back. As time goes on, it supports less and less current. So this current is limited by the transistor itself. This is known as current collapse. So here I have massive dissipation because I have simultaneously 350 almost volts, and I've got 50 amps or something like that. So I've got probably each division here is about 5 kW, 5, 10, 15, 20, 25 kW of peak power dissipation in the device. This isn't going to last for too long before the device is destroyed. If I kept this on a little bit longer, it would completely fail. So this is almost like a short circuit test that I'm showing you here, but the key is that when you exceed the rated current limit, it's not just a linear thermal problem that, oh, I'm 10, 20% over and it's okay. It's not okay, because once you exceed that saturation threshold, the transistor opens back up. It doesn't support the current anymore. And if your current loop is waiting to reach a certain current and you never get there, it never turns off, you could say that this transistor isn't going to last. So you have to know what the current limit is, and you have to be able to accurately measure it to avoid this condition. So there's a couple of common mistakes that will lead to even inadvertently exceeding the current limit. So one of them is that we often measure the inductor current, not the actual switch current. And that's not always the same, especially because there are other things going on dynamically that make the peak current maybe higher than you might expect. So for example, there are capacitive transient currents adding to the inductor current. I'll show you those. Furthermore, the inductor may be hitting saturation, right? When you're at the limit of maximum current that your power supply or converter is designed for, usually to save money, the inductor is designed to approach saturation at that point. So you can end up with a condition where the inductance is dropping, current is rising even more quickly. It's a positive feedback loop there that really rapidly accelerates the rise in current. And then the other thing is just the accuracy and the bandwidth of your current measurement, and the delay time in detecting that maybe there's a fault current, and how much time am I allowing to recover from that and act on it to shut things down overcurrent. So all of these play a role in, you could have a sum of all of these things going on at the same time. So you might think, oh, my inductor current is 35 amps, that's okay. But in fact, the peak current could be double that because of an accumulation of small errors here. And then finally, you may have the condition where the opposite transistor during the transition partially turns on because you haven't driven the gate correctly, and that leads to a partial shoot through, again adding more current than you expected based on the model you might have of this drive. So let's look at these. If I again take the half bridge and I now measure current, and again I didn't show the shunt here, but this is the same circuit we were just looking at. Here's the DVDT in the magenta color. This is now at 5 nanoseconds per division. This is a pretty fast transient. The DVDT is at about negative 70 volts per nanosecond. And I'm measuring the drain current of Q2 with a shunt. That's the blue here. So this is at 5 amps per division. So here's 5, 10, 15, almost 20 amps peak, right? So think about that. If my transistor limit is 40 amps and my inductor current's 30 amps, and I switch on quickly in hard switching, what is the peak current going on at that moment? Well, it's going to be 40 plus this 20, 25. it could easily exceed the device current limit. Now, really short transients like this are usually squashed. In other words, you end up not hitting this peak, and the transistor will just slow down because it's approaching its own saturation. But you have to think about this, that I'm discharging parasitic capacitance in my inductor, in my PCB layout, plus I'm discharging the capacitance of the opposite transistor. Those currents are what's summing into the transistor itself. Notice that we're not even looking at its own self-discharge current, which could be another dozen amps or something like that, because it doesn't show up in the shunt measurement. If I multiply these together here, you can see the peak power. Yeah, it's multiple kilowatts anyway during this short transition. So that's the capacitive current that gets added due to just the opposite device and the parasitics. Next, let's look at the abnormal operating condition of the circuit. So in a PFC, for example, in one of the other videos we went through this in a little bit more detail, the normal operating currents might be on the order of 25 amps, something 20 amps here, peak to peak. You can see here. Now, if I get a line cycle dropout, now I have to recover from that. The circuit is at its absolute limit. It's hitting current limit every single cycle. And my peak current, now this is actually looking at the input current, not even the inductor current. The inductor current is probably going to be even greater than that. I have ripple current here going on. And remember, I mentioned earlier saturation. Well, the saturation could drive this even higher, right? So I have to know what is my real inductor current, how high are these peaks and how high are these peaks, because again, I could be bumping up against the device rated limits, and I want to avoid that because otherwise it's going to desaturate and go into a thermal, runaway condition. I also mentioned the issue of what happens if the opposite device partially or even fully turns on, giving you a shoot-through. How does that happen? Well, this is a complicated looking slide. I'll simplify this. Let's say this is my low-side transistor, and this is the model of it here. And this is my gate drive circuit, including the layout of the PCB and all the parasitics. Now the high-side transistor right above here turns on, applies this fast-rising 100 volt per nanosecond dVdt. What happens inside this transistor? Well, I'm trying to pull this node rapidly very high. What that does is it injects capacitive current into the gate through this gate drain capacitance, which is not a small charge. It may look like a small capacitance on this curve. It is, but remember, this is 400 volts here. This is 1 volt here. So forget about capacitance. Look at charge. It's the charge ratio of these two that matters. So fast rising transient injects current spike like this. My gate drive circuit needs to keep the voltage here below a volt, despite the fact that I'm injecting this narrow, really difficult current spike. So I need to have a very low impedance gate drive circuit and be able to manage that VGS. Otherwise, this will partially turn on and I'll have this shoot through adding to the current that the opposite device sees that's trying to turn on. So in order to mitigate this, we often use negative gate bias. In this example, I'm showing a minus 2.5 volt bias. So in this case, the low side transistor is turning off. It crosses 0 here, goes down to minus 2.5. Then, after some short dead time, the high side turns on, as you can see in the cyan color. And the switch node follows. This is that 100 volt per nanosecond like I just showed you, right? Well, this is the result. In the green curve on the low side, you can see the gate bounce voltage essentially that's nearly hitting the threshold. If I didn't have this minus 2.5 volt bias, this would fully turn on the opposite device, right? The low side device. So this is what I mean when I say the fast switching transients can cause a momentary shoot through of the opposite device that will add to the current peaks, making life difficult for you trying to keep the device out of saturation. So not only do you have to worry about the datasheet limit that says whatever, 60 amps is the limit, I could perhaps make that limit lower, inadvertently by some additional mistakes. One of the most common is not driving the gate hard enough. We should also avoid diodes in the turn-off loop, or that will lead to what I just showed you, the spurious turn-on. And we need to make sure that we reset the capacitor in the RC network every turn-on cycle. Otherwise, that can lead to insufficient turn-on drive. And that means that if you haven't turned on the transistor properly, that limit, that ID pulse limit, is going to be even lower. And then finally, in current mode control, you may never reach your target current if it's set, beyond the capability of the transistor, given all these other factors we just talked about. As far as the gate drive circuit, we talk about the GIT being a current-driven device. And we do that by having a voltage gate driver through an RC network that provides this steady-state current shown in the red path here. But the value of the VCC of the gate driver here, shown as VP here, is a strong influence on what that current source looks like. So here's an example. Let's assume that we have a 3.5 volt drop on our GIT gate, which is a typical number, and I'm varying the supply voltage here. I start at 6 volts, I go to 8 volts, 10 volts, 12 volts. In each case, I have to adjust the resistor to get the same 20 milliamp current, right? So my center point here with zero drain current is 20 milliamps. That's my target gate drive. Let's start with 12 volts in green. If I have 12 volts, no problem. As the current through the transistor goes up and down, what happens is I modulate the VGS. VGS is a function of drain current in GaN. Whether it's GIT or even the Schottky gate, they both have this behavior that the channel voltage underneath the gate varies depending on applied drain current. So if I have 35 amps of drain current in the forward direction here, this voltage is not 0 anymore. Let's just say it's 1 volt. So that means that I was counting on 3.5 here to calculate my resistor. But if it's 4.5 volts, now the resistor value is too large. So as my drain current increases, gate drive drops off. The exact opposite of what you want. What I need is I need to make sure that I drive the gate adequately at the highest drain current. So the lower my VP, the lower my gate drive supply voltage, the worse the slope is here, and I can quickly fall to an inadequate gate drive. I think this is mostly a result of users who are familiar with driving the conventional Schottky gate are always warned, don't go over 6 volts, right? So they tend to use a 5 or 6 volt gate drive and then apply the RC network to make it into a current source. Don't do that. I recommend you need at least 8 volts of gate drive in order to properly drive this RC network. Preferably 9 or even up to 12 will give you a nice flat curve so that your gate drive doesn't vary as a function of drain current. I mentioned the diode and the return path. If I use a gate driver that only has a single drive pin, both sourcing and sinking current, I have this problem that I can't have a separate impedance, a separate resistor for the turn on versus turn off direction. So I only have a single resistor. I can bypass it with a diode or I can bypass with an RC. You can do this, and this is very commonly done with silicon or with other high threshold transistors. What's the problem if I try to do that with GaN? Well, remember, the threshold here is only about 1 volt, maybe 1.5 volts. If I add a diode drop here, I'm now giving myself even less headroom. If this is a 0.7 volt drop, I've cut my margin in half, right? Whatever happens here, trying to pull the gate on, even if I have zero impedance here, I've already lost almost half of that through the diode. A better approach is to use a driver that has 2 pins. And here, I can either use zero impedance or a smaller value here for the turnoff resistor, and my turnoff path is much more direct now, and I can go to my negative bias, whereas here I'm just showing, zero bias with a diode. So this is not a recommended approach to use for high current GaN gate drive. Another potential source of error here is that would lead to problems at turn off of the system is, as we recommend, using a split supply, a +9 and a -3, for example. What I'm showing in this simulation here is that if I start out with the capacitor for the +9 and the capacitor for the -3 equal, so if I have 1 microfarad here and 1 microfarad here, what happens? And this is the gate drive current. This is the bias current for the gate driver. All right, what happens? I turn on, the +9 comes up, and this is my oscillator that's the charge pump charging up these capacitors. I get my -3, I get my +9. Now you pull the plug, power supply is powering down. What happens next? The decay, the RC decay, when I have the same value capacitors here, I get this behavior, and it's the same on the plus supply pretty much. This follows down here. You can see it's approaching 0, and then it even goes negative here. But the negative supply, the dotted line here, goes above 0. And in this region here, I have both the positive gate supply and the negative gate supply for the IC are both positive. Right? So this could lead to an inadvertent turn on if you aren't careful. However, easy fix. I just have to make the value of this capacitor smaller than this. What I'm trying to do is essentially equalize the charge. I want to make sure that the charge of C2 and the negative voltage is greater than the charge on the positive side. When I do that, the negative stays negative as you power down, and the positive even comes down and meets it at this point. So you're sure that the gate drive supply is always negative and you don't risk a spurious turn on. Here's an example showing the gate drive circuit that we use in our reference designs. This is a gate driver that has a fast clamp so that even without power, we can make sure to keep the gate to Kelvin source here clamped. And I have the asymmetric capacitors I just recommended. I have the RC network. I have a nice +9 here and a -3. And I've added this diode D3. This serves to rapidly reset the charge on C16 as I turn off. It means that regardless of duty cycle, even if I'm at 5% or 95% duty cycle, I will always be ready that C16 will be reset and ready to go for the next turn on for both high side and low side. So those are the key points to remember. GaN, the GIT specifically, it's a very rugged transistor as long as you stay within its limits. As soon as you exceed that current limit rating, it'll desaturate, and that leads to this catastrophic failure. The other thing is that overvoltage is rarely a problem with GaN, because even a 650 volt rated GaN transistor is rated for 750 and 850 volt peak overvoltage. So it can take quite a bit of overvoltage without damage. And the GIT gate is also extremely rugged. Because it's a self-clamping gate, you can't overvoltage the gate. It's impossible to overdrive it, unless you exceed the current rating in driving it. But in fact, the opposite is often the problem. insufficient gate drive is the number one reason, in my opinion, why we see failures with GaN, is that it's not driven hard enough to support the current that's being demanded in the application. All right, I mentioned VDS over voltage previously here. What typically leads to the catastrophic failure is desaturation, meaning simply that the transistor is unable to support the peak current that is occurring at that time with that gate drive. And it's either because it's being driven outside its limits and it is getting enough gate drive, it just can't support it, or because the gate drive isn't adequate, can't support the current, and it leads to essentially operating in the linear region. That's what happens when it desaturates. It far exceeds the SOA limit and therefore results in failure. So ensuring proper gate drive under all conditions and keeping the peak current within the device rating is key. And with that, you're on your way to success designing with GaN. Take a look at the other videos in this series that talk about PCB layout, gate drive, and other topics related to GIT. And we're here to help you successfully design with GaN.